Okay, I'm going to show you some things about solving equations. And as you can tell from watching this, it's going to all be off the top of my head. So I apologise in advance for making mistakes, self-correcting. And because the last problem that I'm going to tackle is incredibly difficult, and I've not actually solved it at the whiteboard like this before. Hopefully this will be the first time. So I'm going to talk to you about solving polynomial equations and algebra. And what I'm going to try and do is extend the first method that I was taught at first to solve linear equations. I'm going to extend that to quadratic and cubic equations by using one trick. I call it a trick. One simple trick that mathematicians don't want you to know. They probably do want you to know, they just may not have noticed it themselves, and I'll be honest, I'm pretty sure this is all quite well known. I've just never seen it taught this way, and I think it's useful and instructive. So I can definitely solve all the equations up to order 3. I'm really confident about this, up to the cubic equation. I'm going to start by covering the original problem that I was introduced to at school, which is broadly getting all the x's on one side of an equation and everything else on the other. This is for solving linear equations, equations where the highest power is the power of 1, just the term, the unknown term x. And I'll work through a practical example of this quickly that doesn't involve the division. I'm going to say 3x minus 2 is equal to 2x plus 5. I already know the answer actually after writing it. I chose the 3x and 2x so that they will reduce down and avoid the division. And having done this enough times, I know what the answer is going to be. But let's work through this. So the way that we rearrange equations is that if we take a term to the other side, we swap the sign. And this is a special case of doing the same operation to both sides of the equation to maintain the equality. And you can probably imagine if we add the same number to both sides here, we still maintain the equality. Anything plus 1, if anything is equal to something else, well, then something else plus 1 is equal to anything plus 1. So we want x's on this side, numbers on this side. So let's start by getting rid of the minus 2. How do we do that? We add 2. We get 3x minus 2 plus 2 equals 2x plus 5 plus 2. These two terms cancel, and we're left with 3x equals 2x, and let's add 5 and 2 together, plus 7. You can probably now more easily see what the answer is likely to be. This is 1 more x than we have here, and the difference is 7. So we can see that x is probably 7. This is kind of the same reason I could see it here. I knew that I'd move this over here to do a plus, so it 7. Now, we want to get rid of the 2x here by bringing it over here. So we do the same thing, although because we don't have a minus sign that we can add to, we have sort of an invisible plus sign here. If we subtract 2x from this, we'll be left with 7. So we have to subtract 2x from this other side to maintain the equality and get 3x minus 2x equals 7. We could remember some rule about subtracting multiples. Instead, I'm going to remove the common factor of x here. This is something times x minus something times x. We can write this as 3 minus 2 times x is equal to 7. This may seem like a pedantic level of detail to go through for such a simple equation, but I just want to cover all of the building blocks here, the algebra that we need to do to manipulate these things. And instead of using a rule about subtracting multiples, we can just do basic arithmetic inside of these brackets. And well, 3 minus 2 is 1. And 1 multiplied by something is always itself. We're left with x equals 7. Now, we can check our answer quickly using the original equation. So 3 times 7 is 21. Minus 2 is 19. Sorry for not doing the takeaways and carries. It was a bit too easy. I hope that's okay. 2x plus 5. Well, 2 times 7 is 14. Plus 5. 4 plus 5 is 9. 19 again. And 19 is definitely equal to 19. So we can satisfy ourselves that x equals 7 is in fact the answer. Now I purposefully chose 3 and 2 to reduce to 1 here to avoid talking about the division in the first example. Division is not always as easy as it seems. It's one of the more difficult operations to evaluate and understand. So let's try a more complicated example where we don't pick 3 and 2. Let's choose 7x minus 12 is equal to 4x plus 15. I won't lie, I've chosen the numbers here so that we'll get a whole number answer. 7 and 4 have a difference of 3, so by making this a multiple of 3, as you'll see in a moment, we avoid any weird fractions. Do exactly the same thing that we did before, but perhaps without writing out so many steps in full. So adding 12 to both sides, 7x equals 4x plus 27. You may already see the answer. Similar to last time, we've got a difference of 3 x's here. So we know this is 3 x's. Well, let's qualify that by doing the subtraction of 4x. We get 3x equals 27. So therefore x equals 9. 27 divided by 3. We can verify this as well. 9 times 7 is 63. Minus 12 is 51. 4 times 9 is 36. Adding those together, we have to count 1 there. 1 is 5, get 51. Now, this step here is a form of the general linear equation, this particular case. And whenever we do this kind of rearranging, what we're left with, just before we finish the solution, is an equation that looks like this. We solve it by dividing. And this division is in fact equivalent to a process that we can call removing the lead coefficient from a polynomial equation. It's quite a good idea to do this before trying to solve any polynomial equation. But in this case, we've got the simplest case, the linear one. Now, I'll quickly digress into how this is written as standard. And it's something like this. I've used different coefficients necessarily. so it's easier to understand what's going on, not get confusing. And here, notice that we have an operation in the plus that we lack here. We have an extra term in the 0 that we lack here. We can rearrange this into this, and we do it by subtracting q from both sides. Px equals minus q. So we can say in this case, well, let a equals p and minus q equal b. Sorry that I wrote those in the opposite order. A small mistake. Let's fix that. B equals minus q. Again, this is very trivial, but I want to walk through these steps slowly so you can understand. And so this is a perfectly fine way to write the general linear equation. We normally write like this, and there are good reasons for writing it like this: computer representation, solving things by factorization, probably some other things that I'm not remembering. And so we can satisfy ourselves that this is a general linear equation, and that the process for solving the general linear equation is to divide through by the lead coefficient, in this case a, and gives us x equals b over a. So that's linear equations, the simplest case of polynomial. Let's take a look at quadratic equations. Now, I like a different form of writing them to the one you encounter at school. And there's a good reason for this as well. So I like to write them in this way because it makes them amenable to solving by basic algebra, rather than memorizing a fancy equation. So I'm going to talk about the fancy equation first. Let's just remove this for a moment. I'll use the dreaded red pen, the red pen of shame. This is the form in which we encounter this at school. You probably noticed it's longer. It has an additional parameter. There's a c, not just an a and a b. There's an additional operation in a plus, and there's an additional term in a 0. But what this lets us do is use the equation that they teach us to memorize at school. Looks like this: x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. You might remember this and think this is easy to remember. A lot of people forget it. I work in software development. I've encountered a great many very intelligent and very capable people who forget this. And it doesn't really harm their ability to work, but I've seen a lot of people cast shade and judgment of stuff like this. It's unfortunate. Now, there are a number of problems with this. I'd say you've got too many minus signs. Minus signs are easy to screw up. And you've got one more parameter than you really need. So I'm going to justify my earlier form. I'm going to change the coefficients because I want a and b for myself. These guys can use their p's and q's. So how do we rearrange this? Well, I'm going to take the same approach, except I want to get the highest order term on one side and everything else on the other. And so I'll subtract qx and the r, and this will eliminate the 0 as well, at least notationally. And we will get px squared equals minus qx minus r. We now apply the approach that we used to solve that general linear equation and divide through by the lead coefficient. You might see why it's called this now. It's the foremost, the one at the front. The left is the front, which, because we write left to right, makes sense. And what we get then is x squared equals minus q over p times x minus r over p. And then we can say let a equals minus q over p and b could be minus r over p. And what we have is x squared equals ax plus b. Hence justifying the simplified form here as being equally expressive. It's a more complicated form here. And just to reiterate, what we've done is reduce this three-parametered, four-termed equation with two operations into a two-parametered form with three terms and one operation. Surely it's got to be simpler. Now, doing rearrangement like this is often the case to get it into this form anyway. And so getting it into this form isn't really that much more work. Perhaps I'm trivializing something by doing it this way. I find breaking the problem down into easy to remember simple steps to be much more amenable to learning than memorizing some large equation, one that I've heard described as monstrous, as simple as you might think it is. So how do we go about solving x squared equals ax plus b? So here is where we get to the one simple trick that mathematicians don't want you to know. It is addition. X equals u plus v as a substitution. The reason this is useful is that we can select v to have some impact on the shape of the equation that will result from the substitution. We can do this because whatever value we choose for v, it can be sucked into the value of u, because the minus v can go into the u to give us x. So we can choose for b whatever we want without damaging the solvability of the equation. And hopefully we can make a choice that in fact improves the solvability. So let's expand this by doing the substitution. We end up with, I'll write this out a little bit more long-winded than I might normally. We end up with u plus v squared equals a times u plus v plus b. We expand with brackets. We'll get u squared plus 2uv plus v squared equals au plus av plus b. Now, this gives us the opportunity, like I said, we want to choose a value of b to arrange some cancellation here. And I want to cancel the 2uv with the au because these are the linear terms in u that we'll be left with if we just have u squared, some v's, a's and b's, then we're golden because we know what a and b are and we define v in this process we're about to do. So what we want to do is to cancel the 2uv with the au. And the way to do this is to say 2uv is equal to au. Hopefully you can see then we can subtract au from both sides. And if they're equal, if it's equal to 2uv, it will get rid of this as well. So to do that, you can cancel these u's, divide both sides by 2. And what we're left with is b equals a over 2. Okay. Let's plug that in. So we end up with u squared plus v squared. V is a over 2. So b squared is a squared over 2 squared. A squared over 4. And that's equal to av, but we know that v is a over 2. So we can write this as a squared over 2 plus b. We're very close to solving this, but remember, we want to have the highest order terms on this side and everything else over here, so we have to take the a squared over 4 over here. This is just a guideline. What I'm really trying to do is get this into a shape where I can whip out my square root and beat this thing to death. Perhaps that's a dramatic way of terming it, but we are in fact eliminating terms. So this minus this, we put it over a common denominator. So we end up with 2a squared over 4 minus a squared over 4. Well, 2a squared minus a squared is a squared. So we end up with a squared over 4 plus b. We could take the square root, come off the squaring. And if you're a computer programmer, this is about where you probably want to stop. This is a very simple expression. You know a and b, you can square a divided by 4, add b, take the square root, gives you u. You know that x is u plus b, and b is a over 2, so you take a divided by 2, add it to the value you got for u, and now you've got x. Now, I'm going to make the effort to put this into a similar form to the monstrous equation I showed you earlier. The way I'm going to do this is by simplifying this somewhat into a similar form. I'm going to multiply b by 4 over 4. In fact, it's already multiplied by this because that number is 1. And this will enable us to put these two terms over a common denominator. You may remember this from school and adding together fractions. And we're going to take the square root again. Now, the square root of 4 is 2. And the square root of this is, well, the square root of this. So we can reduce this a little bit more. Well, we actually are after x, and we know that v is a over 2, conveniently already over a common denominator. So we can write x equals a, and when we add the square roots, and the square root has two possible values, the plus or minus notation is useful. So we'll reintroduce that. That does introduce a minus sign. Yeah, we can't always avoid them. So we end up with a plus or minus the square root of a squared plus 4b all over 2. You can memorize this if you want. It's much more amenable to memorization than having extra terms. But this process, I'd recommend understanding and being able to follow through, because we can do this step by step instead of having one big thing that we do. And like I described, we don't even have to do this. We can go back through these steps. Now what we've got here is an equation that has one less parameter than the standard form of the quadratic equation solution. There's only an a and a b, there's no c's. And what's more, we've managed to eliminate all of the minus signs, which, aside from making it easier to remember, makes it less prone to error. And in fact, when it comes to that big equation that I wrote earlier as the solution, the most common mistake I see people making is to have b squared plus 4ac under the square root sign. It's a very easy mistake to make, it seems. So we've solved the quadratic equation with one simple trick the mathematicians don't want you to know. I use that because it's a link bait name. I'll probably title the video that. So how does this help us with cubic equations? Well, this process that we've just gone through, you can actually use it to remove the linear term from any polynomial or the second highest order term. I don't know how to solve the cubic equation by removing the linear term off the top of my head using the same method. So what I'm going to do is suggest that we want to get a cubic equation into this form. you'll notice there's no quadratic term. So I'm going to justify that. I won't repeat removing the lead coefficient again. Sort of busy work. Let's call it an exercise for the reader, as a maths book would, even though we've been through the same process twice now. Let's start with this, which hopefully is convincingly, after that work, the general cubic equation, complete with quadratic term. I'm going to use the same one simple trick mathematicians don't want you to know to get rid of this, or at least get rid of the quadratic term and turn this into the form that I just showed you. In fact, I'm going to use the same kind of notation as I used to show you the rearranging of the linear and quadratic equations so that I don't recycle any coefficients and there's no chance of confusion there. So here we have a P, a Q, and an R. So let's write out our trick. Now, this is a special case of what I think is called a Sheeran-House transform. There's more complicated ones. You can have a quadratic substitution here, for instance. I won't talk too much about that. So let's expand these brackets. I'll write this out a bit longhand again so you have at least some idea of the steps involved and I don't just gloss over stuff. Expanding this. Well, I won't do the whole diagram, and I know from experience how to use Pascal's triangle for this and done it too many times. U cubed equals equals indeed. U cubed plus 3u squared b plus 3ub squared plus b cubed is equal to. It's very unsightly when the equals just don't line up. I'm usually a bit better at aiming that. Let's try it again. U cubed plus 3u squared b plus 3ub squared plus b cubed is equal to pu squared plus 2pub plus pv squared plus qu plus qv plus r. And if we're going to select v in the same manner as before, we want to eliminate the u squared terms. There's one of the benefits I find of this notation is that, I mean, you can do it the other way as well, but you can cancel these terms with each other to sort of get rid of them. And we do that by saying 3u squared b is equal to pu squared. We can cancel the u squareds and we can divide through by 3. We get b equals p over 3. Now, although hopefully I've shown you that it's reasonable to expect these terms to be eliminated now, and we can solve the simpler form, which is called a depressed cubic. Sounds rather sad, but it's a rather joyous thing, in fact. I'm going to do the horrible work in front of you. I usually avoid this. I'd say leave it as an exercise for the reader, but that's not exactly a great way to build faith, is it? So we know that these two terms are going to disappear because by design, choosing b equals p over 3, that will happen. Our u cubed over here remains. 3ub squared, well, that's going so tempting to write the equals first, so rearrange it so often in that way. We'll end up with u cubed plus 3 times u times p over 3 squared. So that's 3u, 3pu over 3 squared is 9. 3 and 9, well, we can reduce this to p over 3u plus v cubed. It's going to be p cubed over 27. Sorry, this should be p squared. I told you I'd make mistakes. Hopefully this is useful, because as much as I've done this a billion times, I still make mistakes. Everyone makes mistakes. Although with practice, we can reduce that frequency. Okay, so that's this side of the equation. And what is this equal to? Well, we've eliminated the pu squared, but 2puv. Well, v is p over 3, so we get 2p squared over 3 times u. You'll notice there's something here. I'll come back to that in a moment. Plus pv squared. Well, p squared is p squared over 3 squared, p squared over 9. We've got another p there, so that's plus p cubed over 9. Qu remains Qu. And Qv is going to be Pq over 3. R remains R. Okay, so we want to take these things over here. Conveniently, these are already over a common denominator, and p squared over 3u. 2p squared over 3u minus p squared over 3u is conveniently p squared 3u. Sorry, p squared over 3 multiplied by u. So the reason I'm keeping it like this is I'll put our a's and b's in a moment to justify my simpler notation. So we've gotten rid of this one. What about this one? Well, there's something else I want to do first, actually. I'm just going to move this forward so that we've got plus QU. And in fact, we can extract the common factor of U. Sorry if this is doing a bit much at once. I'm blessed with the good fortune of being able to keep track of such things. And this is when I'll make a mistake after making such an arrogant statement. So this is the linear terms all organised. Now this p cubed over 27 is going to have to come together with this p cubed over 9. Well, making this into something that has a 27 on the bottom, we multiply the top and bottom by 3 because 3 nines is 27. You could divide 27 by 9 if you don't have such good intuition for multiples there. Nothing wrong with not knowing your times tables, as long as you can multiply and divide. So what we end up with then, subtracting that, is plus 2p cubed over 27. We've got our pq over 3. Now we could put these over the common denominator if we want as well. It feels a bit excessive at this point. And well, we've gotten rid of all those, so we can just write our u cubed here finally. Could have done that at the last step. And our r. And well, now we can say, finally, let a equals p squared over 3 plus q, and b equals 2p cubed over 27 plus pq over 3 plus r. And what do we have? U cubed equals AU plus B. Now we've ended up with U's instead of X's, but this is exactly the depressed cubic we were looking for. It's kind of a miserable name. I'd like to call it the fun cubic or the awesome cubic, because it's so much more solvable. So I'll show you how to solve that. And again, we've broken this down into steps. This is quite a lot of algebra, but it is simple algebra. I didn't have to memorize anything to do this. I just had to know the basic rules of substitution, multiplication, addition, how to put things over a common denominator, how to expand brackets. Okay, so I'm glad I didn't leave that one as an exercise for the reader. How do we solve this? Well, I'm going to use that one simple trick the mathematicians don't want you to know. I'm going to have to rewrite some things, but hey, such is maths. Okay, let's expand these again. I won't bother writing out the bracketed form. I did that last time. And we end up with, again, u cubed plus 3u squared b. I'm sorry to reuse u and v. Hopefully it's not confusing. Plus 3uv squared plus v cubed is equal to au plus ab plus b. Now, this isn't quite immediately obvious how to deal with this. Now, what I notice, hopefully this isn't too much of a stretch, is that this here is a common factor that can be removed. There's a common factor that can be removed here. To put it back to something close to this, in fact, the right-hand side is going to become the same. A times x is a times u plus v. So I kind of didn't really need to expand those brackets, could have left it like this, because, so this is 3uv times u plus v. It's a convenient way of writing this. We've got a v cubed and a u cubed. Now, this is a bloody nuisance, as is this. Now, if we choose v appropriately, even if we involve u, we might have a good chance of solving this. And in fact, the way we're going to do this is we're going to cancel these two terms by setting 3uv equals to a. So 3uv, you know, I'm going to write it up here like I did last time. Let 3uv equals a, and we can cancel these, and what we're left with is then b equals u cubed plus v cubed. And so we've now got two simultaneous equations. I slightly regret writing it up there. I'll just rewrite them again. A equals 3uv. B equals u cubed plus v cubed. This is eminently solvable, and we're going to do it by setting v in the same way that we did before, although it's going to become, in terms of u, we can't cancel all the u's like when we removed the term from the equation. We divide both sides by 3u, and we get v equals a over 3u. We plug that into here. Well, b cubed is now a cubed over 27u cubed. So we get b equals u cubed plus a cubed over 27u cubed. This looks a little bit horrible. So what we're going to do is get rid of this division by u cubed by multiplying through by u cubed. Both sides, we multiply both sides of an equation, it remains equal. And we get bu cubed equals u to the power of 6 plus a cubed over 27. Now, this is a quadratic equation. It might not be obvious that it is, so I'm going to make a substitution to reveal that. Let w equals u cubed. We get bw equals w squared plus a cubed over 27. Let's put that into the form that I like. I'm just going to flip that around. So you've got the w squared on this side. It's equal to bw. And if we subtract a cubed over 27 from both sides, you get bw minus a cubed over 27. And what letters shall I use now? Let's use R and S. Although B is perfectly adequate as it is. Let R equals B, S equals minus a cubed over 27. Then we have W squared equals RW plus S. This is the X squared equals AX plus B that we solved before. Now you notice that there's two solutions to this. I don't particularly want to go through the whole rigmarole of demonstrating this, but in fact, one of them is U and one of them is V because there's symmetry between U and V. Notice if you swap one for the other, the equations, every equation involving them, including these ones, remain exactly the same if you swap V and U. So whichever solution we get, we can then take the cube root of to find U. In fact, I'm not going to give you the long-ass equation version of this. I don't think it's helpful. I'm just going to say you're a computer programmer. You've probably written a load of functions to not have to wrangle all of this into a mathematical equation. So you solve this using that quadratic equation solution that we had from before. And we know, okay, so W is equal to R plus or minus the square root of R squared plus 4S all over 2. Because we know the symmetry, we can eliminate that pesky minus sign even. Isn't that beautiful? And so we could use the symmetry here to have the minus sign be the other one, but I'd actually suggest using b equals a over 3 times that. Because we've already got it. Doesn't rely on complicated, weird symmetry arguments. And so we can work that back through to find x. And that's how you solve the cubic equation using one simple trick that mathematicians don't want you to know. Now, the thing I talked about earlier, the difficult bit, the tricky one, is solving the quartic equation. I am not familiar off the top of my head with how to reduce the quartic into anything less than the depressed quartic, which I kind of want to call a happy quartic because it's happier than the original form. Certainly easier to solve, more amenable, more friendly, the friendly quartic. So I won't bore you with a ton of basic algebra again. I've not quite worked out how to do this from my preferred form, so I'm going to go with the more classical form here. Well, I've still remove the lead coefficient in the cubic term. Hopefully I'll work out how to make this more attackable. So how do we approach this one? Well, I've had an attempt at this a few times. I think I've got the shape of it. Hopefully this time I'll be able to run it all the way to the end. And you can watch me make a lot of mistakes and get very confused. So the way that I approach this is I want to factor this into 2 quadratic equations because quadratic equations can be solved. If there's 4 roots, it seems pretty reasonable. There's a load of complicated theories that you may have heard of. I can't remember, is it the fundamental theorem of algebra that says that you can represent this as a load of x minus roots multiplied by each other? Well, each pair of them gives you a quadratic. So I'm going to give you p's and q's again. We write this as x squared plus px plus q. multiplied by x squared plus rx, sorry, getting ahead of myself, plus s is equal to 0. That will give us two equations we can solve separately using the quadratic solution. Fantastic. Now, let's expand this out and see what we get. And the missing cubic term is going to help us because it's going to give us an equation that's equal to 0 here, which will round it out hopefully enough to solve it. Or at least this is the feeling I got last time. Well, I got a little bit lost after that point because it's quite tricky. So I'm going to multiply this by each term in this. So multiplying all these by x squared, we get x to the 4 plus px cubed plus qx squared. Multiplying this by the rx's, we get plus rx cubed plus prx squared plus qrx. And then all of the s's, we get sx squared plus psx. I want to make a PlayStation joke. It's nice to see those initials come up in a context that isn't my game development job. Where were the sqs? On the end, that's equal to 0. And we can group the like terms together. So we end up with x to the power of 4 plus p plus r x cubed. So we know p plus r equals 0. No x cubed terms here. And in fact, we can just not write that and just write this. God, that is one flat looking 0. Okay, so we've got p plus r equals 0 over here instead of bothering to write that cubic term. Then we've got qx squared, sx squared, and prx squared. So that's p r plus q plus s multiplied by x squared. So a is equal to pr plus q plus s. If p plus r is 0, p equals minus r. I don't think I like r very much. Let's get rid of r. I'm trying to eye up if r is going to come back and bite me here, but I don't think it will. So we can actually write this as q plus s minus p squared. Because p is minus r is equal to minus p, which means pr is equal to minus p squared. Okay, so we've got the b next. Where are the linear terms? QR and PS. Okay, that's quite simple. So we have QR plus PS equal to B. And, well, P equals minus R. We can write this as, in fact, PS minus PQ. We can extract the common factor of P here. P times S minus Q. That may be unhelpful, we'll see. Let me just write that so just better. This long-winded thing here, so what was it? QR and PS. I'll write them that way around because then there's a symmetry there. We've got P beginning Q, beginning P, beginning Q, and then the S. And, well, p is equal to qs. It's the only constant term we've got. And that's all equal to 0. And we can write qs equals c. Now, how can we attack this? This is kind of where I got stuck the last time. I tried a few things but didn't really resolve it. But it feels like there should be something that we could do. So this qs, we've got a q plus s, and s minus q. I feel like I want to try and turn this into something involving some squares, because they're much more amenable to working with than things that obviously aren't squares. I can't help but notice that, well, if we do q plus s squared, that's equal to q squared plus 2qs plus s squared. This is 2c. So we can write 2c here. The s minus q feels annoyingly the wrong way around. We can square this. Let's divide through by the p. I think this is going to work anyway. I've just written this in a bad way around. What I want to do by accident. Divide that through. But I'm going to leave these equations here as they are, because they equate with those coefficients. But what we can do is say, well, let's do s minus q squared. And that's equal to q squared minus 2c again. It's 2sq plus s squared. And we can subtract these. I think I'm getting there this time. I think this might actually work. It's the first time I've done this. It's probably not going to work. I'm going to eat my words in a minute. So divide this through by the p, and we have here b over p squared is equal to this. And I'm going to subtract this q plus s, which is in fact a minus p squared with this equation here itself squared. This is where I'm probably going to turn it back into the same quartic I started with by accident, so you can have a good laugh at me now. Let's see, so subtracting these. Okay, so we've got our, I'm going to have to make some more space. I'm going to just like move over and cover my writing somewhat as I do this. So I'm just going to try and make it obvious that this is the direction we're going. So we've got b over p squared. And we've got a minus p squared squared minus a minus p squared. So what I'm doing here is I'm reducing this to just an equation involving p, so we can solve for p. Once we solve for p, we can find everything else, we hope. I hope. I'm not sure that's possible actually, but let's carry on. Let's see. Hopefully this is somewhat instructive as to the process that we could use to tackle an unfamiliar problem. Because that's, I mean, I've tried this a few times and screwed it up. It's not easy. So this is our difference of these things. That's equal to -4. Wait. Subtracted that one from that one. If I do it the other way around, it would be a plus. I like my pluses. I like my pluses quite a lot. Okay, let's do that the other way around. Sorry, I just had to justify that to myself a little. And okay, so let's do the q plus s bit first. That's equal to a minus p squared, a minus p squared squared minus b over p squared we can't get rid of this minus because the difference of squares is kind of fundamental to this wonderful trick that I'm trying to employ. That's equal to 4c. Actually subtracting this from this. The q's and the s's are gone. And in fact, I'm looking at this and thinking, should be able to solve this now. It's not entirely going to be pretty, but it should work. So let's rewrite this bit here as b squared over p squared. If we expand the a minus p squared squared, we get a squared minus 2 a p squared plus p to the 4. That's minus b squared over p squared, which equals 4c. This is a cubic equation, I think. Pretty sure it's a cubic equation. We multiply through by p squared, and we get a squared p squared minus 2 a p to the power of 4 plus p to the power of 6 minus b squared equals 4c p squared. The reason I know this is a cubic equation is this 2, 4, 6. We make a substitution similar to last time, something like w equals p. Then what we get is, if we let w equals p squared, I kind of want to write it in the way that I'd like to write it because it will eliminate some of these minus signs as well. And I'm going to do that in one step. So w cubed from there is equal to, taking the 2ap to the power of 4 over here, it becomes 2aw squared. This isn't going to be a depressed cubic or happy cubic, friendly cubic. It's not going to be one of those. But we can reduce it to that later. That might have to be an exercise for the reader. If I can resolve the rest of this hell of a mess that I've made over here. Which I think I might be able to, actually. I'm not deluding myself too much. When was I? 2aw squared. That's gone over there. And then we've got this term and this term, so this is going to be 4c minus a squared w. And this b squared that we've got left becomes plus b squared. So I've somewhat achieved my goal of eliminating a lot of minus signs. And then we can say, I'm running out of letters. I think I'm going to use some primes in a different colour just to make it clear that I'm making a mess here. We can say, let a prime, looks like a to the power of 1. That's why primes suck. Do I want to use Greek letters? They kind of suck too because alpha looks like a. Okay, let's use Greek letters. Why the hell not? I'll use alphabet. I was thinking I'd use some further down the alphabet, but that'll be even more confusing. Let alpha equal 2a, beta equals 4c minus a squared, and gamma equals b squared. Then we've got w cubed equals alpha w squared plus beta w plus gamma, exactly the form of cubic that we solved the first time. Now, I have some dim recollection of, I worked out how to do this in code years ago. I've not done it in like 15, 20 years, something like that. But I remember there being a resolvent cubic in Ferrari's method. I'll talk a little bit about the history afterwards because it might be exciting. Everyone always talks about it when they talk about these things. I'll give you something other than dry maths as well. So this is a cubic we can solve to find W. If we find W, we can find P. I'm not so sure about the plus or minuses for the P, except that we've got this kind of symmetry again between the P's and the R's. I don't think one of the solutions is P and one of them is R. That'd be too good to be true. And actually, I can see that's definitely wrong because we have got some terms here, quite some terms. It's not going to allow that to be that simple. So we can solve this for W. This is quite involved. You have to do all that substitution that I showed before. And like I said, this is a hard problem. This is the hardest polynomial equation that you can solve without resorting to constructing special functions for doing it. Those functions are more difficult to evaluate than, you know, square roots, cube roots, fourth roots. Well, they certainly can be evaluated. They have no less legitimacy. Okay, wow, this is exhausting and hard. So if we find P, so P is now known. Brilliant. What can we do with that? Well, I think there's something we can do here. We've got S minus Q and S plus Q. Yes, in fact, of course we can. Oh, this is brilliant. I've never solved this one before without enormous amounts of reference material and not being able to remember a bloody thing about it. So I'm quite happy that, I'm sorry to let you down on my, well, now that I've made this arrogant statement, I'm going to work out what's wrong. I'll keep that in blue. It was a bit weird to use the Greek letters, but now we've got P. Yeah, we have P. And we have expressions for Q plus S and S minus Q. What am I going to do with them? Well, I'm going to subtract them from each other. Okay, so these two, I'll do that over here. And hopefully you can still see this. It's getting a bit messy now. It's because I want to save this for the grand finale. Now, we've got S plus Q is equal to A minus P squared. We had that before somewhere. I think I just like absorbed it in the horrendous amount of rearranging I did there. It's this A minus P squared. And we have S minus Q equals B over P. Now, at this point, these are completely known quantities. So if we add these together, we get 2S is equal to, I'm really enjoying this, A minus P squared plus B over P. We subtract them from each other, we get 2Q is equal to, I think this may be where the symmetry of the solving that square root is going to be eradicated. I'm not quite sure about the threefold symmetry of the cubic. I know the fundamental of a theorem of arithmetic is going to resolve this down to having at most 4 roots. So that sixfold multiplicity between those things has to disappear somewhere. I wish I could quantify that better. Wow, this is really enjoyable. Never done this before. A minus P squared minus b over p. And so we can find S and Q. Yes, absolutely brilliant. And we know the relationship between P and R. So now we have P, Q, R, and S. We have two quadratic equations that we can solve, which we've already solved them. I'll leave the rest of that as an exercise to the reader. Despite the fact that I saved this area for a grand finale, I'm realising the enormous amount of maths, the enormous amount of algebra that's going to be required to do back substitutions. Probably not very helpful, but then this does give us the 4 solutions. And I'll write them down. Yes, I have space for a grand finale. Of course I do. We have x is equal to, these are annoyingly, I should have made them minus p, minus q, minus r, and minus s. But hindsight is a wonderful thing that I didn't have because I've never done this before. So it's going to be equal to minus p plus or minus the square root of p squared. We can get rid of the minus p squared is p squared. Minus 4q over 2. That's the solution to this bit. And minus r plus or minus the square root of r squared minus 4s all over 2. Those are our 4 solutions. It's just an underline there to finish framing all this nonsense, not confuse it with our arrow. And that's how you solve a quartic polynomial. And at this point, I'm out of polynomials. The quintic, a young man named Everest Galois showed was not possible to prove using this kind of algebra where you're limited to powers and roots, plus, minus, times, and divide. Wonderful. I've never done this before. I'm going to definitely have to save this video and upload it somewhere. I don't want to wipe it away now. I'm not going to be able to forget this now either because it's not as good as I'd like. I would have liked it if I could have had the x to the power of 4 on one side and the rest on the other. But then that makes a mess of this. Probably do something similar where you take that over to the left and then write that as a product of 2 squares or 2 quadratic equations. I think it would work out about the same. It's slightly disappointing after. So the thing that I really enjoy about the approach that I took here is I took the way to solve the linear equation and used it as the first step for solving the quadratic equation. I then took how I solved the quadratic equation and the linear equation and used them as the first 2 steps for solving the cubic equation. And then I applied the one simple trick again. This has nothing to do with the one simple trick. This is just raw. I mean, it's all raw algebra, really. There's no memorizing. So I remembered this from having worked it out. I could have just rederived it. It wasn't that difficult the first time. So you have it. That's how to solve every polynomial equation that can be solved in radicals up to order 4. There's definitely some other special cases you can solve. Why not? Let's just. I don't want to wipe this off. Do that ridiculous thing where I take a photograph of something I've written. Don't know why it's ridiculous. It just feels somewhat silly. Hopefully my voice comes out well in this. I don't particularly want to voice over it. Wow. I'm 40, by the way. I've been doing this stuff since I was, I want to say 12, 10, something like that. I mean, the early algebra when I was 8 or 9. Nice. I guess I can tick off polynomial equations. I finally maxed out that skill tree. Although I don't know if I'd call that maxing it out. There's going to be some more diminishing returns to be had. Wow, cool. Okay, I'm going to show you some other types of polynomials. Well, I mean, you can probably guess, because what we did here was solve a sixth order polynomial by using a substitution. And I think this is called a bicubic equation, because it's a cubic of squares. When we were solving the cubic, we saw a sixth order equation that could be reduced to a quadratic. And in fact, there's a whole family of these. So I can make a 10th order equation out of this if I want. You may wonder, well, that's not substituting a square, that's not a power to fit here. Well, I could multiply this through by x to the power of 6. Of course, you'd want to divide through by that to get rid of it and reduce the equation to simplest terms. Okay, yeah, I don't think there's too much point talking about that, but I'll show you one other special type of polynomial that my maths teacher showed me how to solve. In fact, when I asked him about all this stuff when I was at school, wonderful character. He did give me a lot of detentions and put me to the side of the class and all kinds of other horrible things, but he did encourage my growth as a mathematician. And he showed me this wonderful class of polynomials that you can solve. It actually came in useful later in an unexpected place of factorizing numbers. So I'm going to show you how to solve a whole class of polynomials of any order now. So imagine you've got this quintic, which looks horrible to solve, just because it's quintic. You might think, well, that's a quintic equation, let's give up. Multiply the whole thing through by x. What do we get? I'm going to write it slightly offset here. Well, what do we get? We get x squared, x cubed, x to the 4, x to the 5th, x to the 6th. Wow, I made it even harder, except we can do something wonderful. We can subtract these two. So if we subtract this one by this one, as in take this one away from that, all of these terms cancel and we're left with x to the power of 6 minus 1 equals 0. Or x to the 6 equals 1. And so the solutions to this equation are the 6th roots of 1. I want to say that 2 of those roots are identical, which then resolves the mystery of why a 5th order equation could have 6 roots. In fact, I feel like we could break that down as the square root of a cube root, the cube root of the square root. Think of this as, I just want to justify that there's 5 roots. And so it's 2 of these. We've got the cube roots of 1 and the cube roots of minus 1. Cube roots of 1, definitely 1 and 2 different complex numbers. So 1, call it C0 and C1. I can't quite remember what they are. I think it's like root 2 plus root 3i or something. So half plus root 3i maybe. So what's the cube root of minus 1? Well, the cube root of minus 1 is minus 1. And it's also 2 complex numbers. Maybe I'm missing something. Is one of the cube roots of the cube roots of minus 1 can't also be the cube roots of 1. How have I introduced an extra root that I can't remove? Yes, obviously. This is wrong. That's the extra root we added. So the solutions to this are, in fact, the cube roots of 1 excluding 1. So the complex cube roots of 1 minus 1 and the complex cube roots of minus 1. Why is it not 1? Well, I'll tell you why. Because 1 plus 1 plus 1 plus 1 plus 1 plus 1 is definitely 6. Sure as hell isn't 0. There we go. That's how you can solve a fifth order equation of a very specific form. You may notice during this multiply through by x that what you can actually do is have coefficients here that are all the same, I want to say. No, that's not quite right. I'm sure there's something there. Never mind, I've done enough. I just solved every polynomial equation that you can, and at least in the general case, and a very special case here. You know, we can add more to this if we wanted. We could have made it a sixth order equation, and then we'd end up with this, and we'd end up with seventh roots of 1, which a little bit harder to work out. Yeah, if we added that, we could do the eighth roots. We'd end up in a similar place, I'd imagine, where we can rule out the 1, obviously, because it adds up. But we'd have, in fact, fourth roots, which are called q's instead of c's, so they're quartic roots. Sorry for drawing triangles and squares, it's kind of like how they'd look on a complex plane in my head. Oh, but of course the fourth roots of 1 would be another minus 1. There's repeated roots in these things. Anyway, hopefully that was entertaining. It probably wasn't very entertaining. Hopefully it was insightful. I'm somewhat overjoyed by that. Not very often that I challenge myself in that way and I succeed. Even right at the end, I was expecting the wind to be taken out of my sails by realising that I'd just gotten back to one of the previous equations that I had. Wonderful. Right, well, done with that.